Testing 1 2. Testing 1 2. Testing 1 2. Okay. In case yazima, you tell me. Ikazima uniuze. Peter. Hello. Okay. The same number. Same number. No, sure. Good afternoon. Oh, it's an evening now. It's both. Okay, so I haven't seen you guys in what? 2 weeks now? Hey, you've been dodging me. Ever since we had our tests. No, but after a test, we had a meeting, right? Yeah, so, okay. Good to see you. Why is this guy still solving the stuff we did 3 weeks ago? Swenzo Bwerate? Oh. Okay. Supposed to be mine? All right, so I hope everything is okay. How are your tests? Not just mine, but any other tests like math and the other stuff that you're doing, the surveying. Who's taking you in surveying? Is it Mr. Shawa or Madam Handongwe? Well, clearly some of you don't come to class, huh? At Wanje? Okay, and I heard that you guys were voting. Like I never slept that night. Whatever you guys were doing the whole night, did you vote in the right people? One is here. Oh, who's that? Hey, that one. What position? Committee member. Okay, cool, awesome. Awesome. Yeah, it's. I think you need to do that more often. You guys should be. I think I always preach this. Try to. Don't go back to your shells. You know, just because you were an engineer, that you're supposed to be reserved. Who told you? You know. So talk if you can talk. If you love talking, do that. It will open doors and opportunities for you, okay? So there are things you've heard about a certain career and then that you can't do. Up until maybe, yes, the profession says you can't do this. Do things that make you feel whole, okay? So well done, you know. It's never easy to put yourself up for certain challenges. I mean, if she would have lost, probably people would have talked enough to a point where she would have heard about it. And just that thought alone, she wouldn't have done it. So, congrats. For me, I always, that's really good. Okay. So, try to remove manta in the stuff that you guys are doing. See, the majority of people are always, they always find the negatives out of everything, you know. no, if I try this, what if it goes wrong? No, like, why can't you think, what if it goes right? And even if it goes wrong, you still learn a lot from that experience. So try out stuff. Try out the stuff. Okay, so if I remember what we did last time, we started talking about the energy equation. Okay, so, but we did this, right? Yes. Yeah, so the next thing is the energy equation. Yes. You were doing what? And we solved it. So it's done, so we need to move on. So, you guys have the module. It's easy to just, okay, this is where we ended. Probably when this guy shows up, this is what we'll talk about. That always prepares you mentally for, okay, if he teaches about this, I have an idea. You don't need to read through thoroughly, just pamwamba surface. You skim through, right? But then for all of you not to even have an idea what an energy equation is, it's worrying. Okay. So the energy equation. So this is supposed to be our last episode. Okay, our last class. But I doubt if it will be. But let me just say it's the last topic. So I'm going to introduce the concepts. We'll talk about the concepts that are involved. And then we'll try to bring up an example. If you have been reviewing some of the past papers, there is always at least a question around the energy equation. You know, I don't know if maybe some of you are going to agree. If you have found something that looks like this, okay, and then maybe there's, not maybe, but there's always maybe a Z1 or a Z2, this being your datum or datum. Have you ever found this before? You haven't seen something like this before? Mr. Robert, you see why he's a class rep? Okay, so the topic about the energy equation is very basic. It's about taking advantages or an advantage of certain parameters about a pipe, and that should inform you of what you can get from the next point. So what you're looking at here, ideally this is a pipe, except this pipe has been truncated or cut on both ends, and from wherever it's been cut from, between position number 2 and 1, this has got a bigger opening compared to that, okay? And some of the questions that would come is that maybe they'll give you the datum, distance from where this point is, and as you can see, there's a difference there. They'll give you the pressure involved, they'll give you maybe the velocity involved, the discharge involved, and then there'll just be that one parameter which is missing. So it's sort of a build-up from what we've been doing the past couple of classes. And from what we've done, we discover that your discharge will always be equal to what? Area by what? This equation is very much important again, but then we're going to implement it in addition to what we're going to talk about today. Okay, so let's talk about the development. Where does the energy equation develop from, and how do we make use of it? So I'm going to dictate a few notes here that are important. So if you do have an example that looks like this, I'll need it. Yeah? So let's write this. We apply the law of conservation We apply the law of conservation of energy, control volume. We apply the law of conservation of energy to a control volume. Full stop. To do so, we must identify the forms of energy in the control volume. We must identify the forms of energy. We must identify the forms of energy in the control volume. We must identify the forms of energy in the control volume. Full stop. Are we there? I know there's a sketch here, but it doesn't even make sense. Okay. Consider the following system. So consider the following system. So say consider the following system with the forms of energy. Consider the following systems or the following system. Consider the following system with the forms of energy. 1, pressure energy. Okay. And pressure energy. So just sketch this somewhere. We're going to make use of it, maybe just after what you've written. So this is just a pipe. It changes in diameter, it grows. And then we've got a datum here. This is Z2 and Z1. And then what you can also write on that part is you can say pressure 2. This is pressure 1. You can say comma velocity 1. This is comma velocity 2. Don't worry, we're going to explain how these just come in handy when you begin to solve certain questions. Okay? So the forms are 1, pressure energy. So after your sketch, I would want us to write something about the pressure energy and what it is. So ideally, at any point that you're going to truncate or cut this pipe, it could be this part or that part, it always has about 3 energies that are flowing in them or in it. So 1, we said pressure energy. So under pressure energy, let's write this. So you can say pressure energy, full colon, or just you can write something below that. So the pressure in a fluid also does work. The pressure in a fluid also does work. The pressure in a fluid also does work by generating force on a cross section. By generating force on a cross section, which then moves through a distance. Which then moves through a distance, which then moves through a distance. Full stop. Can continue and say, this is energy. This is energy since work is energy. This is energy since work is energy. This is energy since work is energy. So that's one energy that you can find, across or along a pipe. Another very important energy that is found, as long as water is flowing through a controlled volume, is the kinetic energy. Kinetic energy. You can put your full colony there, or you can just write something below. So let's write something about that. This is due to the motion of a mass of fluid. This is due to the motion. This is due to the motion of the mass of fluid. This is due to the motion of the mass of a fluid. So just the motion of a fluid, you can get a sizable or a piece of fluid that is moving. And just by virtue of it moving in a certain format, it has or it generates energy, and that is what we call kinetic energy. So the movement due to the mass of a liquid. Then last but not the least, we have potential energy. Okay? Potential energy. Potential energy. So this is due to the height above an arbitrary datum. This is due to the height above an arbitrary datum. So the Z1s and the Z2s, they bring about the energy. And all of the physics that you did way back, we are finding ways of which you can apply that. So this is due to the height above an arbitrary datum. So an arbitral datum could literally be anything. If I wanted, I can put it here. If I want, I can bring it down here. But it's just a reference point from which both of those points are going to be referenced to. Okay? Okay. I don't know how you're writing this, but for pressure energy, this is the formula it comes with. Okay? So it's just basically a pressure over mass density by gravity. So we are back at this again. If you miss the first class of the mass densities, you need to revisit that. Because today we've got a mass density here. In the test, I'll give you just the specific weight, for instance, and hope that you generate your mass density from that. Are we together? So this is the formula that you're going to need. For your kinetic energy, it's always a velocity on top raised to the power 2 over a 2 gravity. And the potential energy, well, potential is just a Z. So Z is usually just denoted, or it's used to denote the distance, the height And it's not always Z, but it helps to solve certain questions. So if you want, you can put your K there, you can put your M, doesn't really matter, but it helps just to work with the Z. Okay, so based on what you are given here as a system that is transferring water, so this is the entry point, and this is at the point where water is leaving. So if I'm going to use this as the first point and the second point, it should be able to give me some results should I be, asked the question. So what I want to do now is the previous class that we had, we talked about the quantity that enters one area. Let's say Q in is always Q out, not so? And this is assumed that there are no leakages, the fluid is incompressible, there's no friction, because with friction you lose energy and then energy just moves around. So what's happening here is that if I get just one cross-section area, at this particular point, there is pressure energy, there is velocity, and then of course there is the Z, okay? This should be equal to whatever is happening at the second point. So if this is the first point, this will be your second point. And whatever energies or equations are happening at one cross-section area, they should be equated to that point. If you're going to equate all the energies at one cross-section area to the next, then you are talking about, I don't know if you've heard this before, but the Bernoulli's equation. We have heard about that before, right? Yes. So this is where we are. So let me just sketch that properly so that people don't. But how is it that you know about the energy equation and not the Bernoulli's? I mean, you know the Bernoulli's, but not the energy equation. When I in the chair fast forward. So everything we're doing is a build-up of whatever has been done. So this is my arbitral line. So I can say this is my Z1. So this is my, let's say, point 1, and then point 2. And then I'm equally interested in this. If this is 2, so this is my Z2. What also this means is that my pressure is at 2 over rho gravity. But then my velocity is equally at 0.2 divided by 2g. Are we together? So the subscripts such as seen here, they're just showing the point cross-section 2, which is here. So if you come to the cross-section point number 1, what you expect is having a pressure at 0.1 divided by mass density over gravity. That's for your pressure. For your kinetic energy, it's going to be velocity is always raised to the power 2, but a subscript 1, because we're at 0.1 divided by 2 gravity. And then the Z sits here. So when you equate whatever is happening here to the other point, the answer should always be constant energy. So just by understanding that statement, it means that you've understood what the Bernoulli's equation is. So we can write whatever is happening here down here. Can I erase this part? So if you have that, and I urge you to sketch it. So we can start with 0.1. So we can say 0.1 divided by gravity, mass density by gravity. We are adding all the energies at one point, divided by 2g plus z1. This should be equal to P2 divided by mass density gravity plus velocity raised to part 2 subscript 2, 2g plus 2 z2, not zz. So this is point number 2. Okay? And what's known is this is always constant, all right? It's always constant. It's also a head, by the way. So much as these guys are energies, they are also heads. So at the end of the day, whatever you calculate, if it's this straightforward, your value here will always be, what are the units for head? It's meters, not so. And that's your energy that you're looking for. So constant, and then of course constant sometimes is denoted by a capital H. And what we're looking at right now is called, this is the Bernoullis equation. But then of course for an equation like this to work, there are always assumptions that are made, and I think we talked about them. Okay. Can I get an example from the past papers? Anybody from what we've done or what you've looked at? Monata avance. No? Someone has? You have? An example that to allow us to apply the Bernoullis. So this topic should be very fairly Do we have anything? No? Let me check if I've got something in the computer. So let's just see how we can apply this. So we do understand where these points are coming from, not so? So this is one cross-section area, we're dealing with one, and then the other one is on the other part. So the energies that are generated on one part or one cross-section area are always the same and very constant to what's happening there, as long as there's some variables that remain the same. So let's see how we can apply one of these. I thought you guys move with past papers. You don't, eh? Yeah, my laptop. So mind that my laptop. Okay. You have found a question? Let me see how it looks like. Let me see how it looks like. Maybe it's the one I'm looking for. No, this is not, we haven't done this. You want to solve this, eh? Or I should just bring it, eh? Question what? Yeah, this is basically the same. Okay. Have you found something? Okay. All right, so I found something. I'm just going to dictate. We can always, let me have your attention. We can always do that one as well. I can give you hints on how to go about it. But let's start with something which is a bit more close to home. Not really difficult, but a bit more close to home, and then so that we open up our minds to other possibilities. Okay? So oil is flowing through. So this is like the reason why I'm using this is because it also includes part of what you've done from the other topics. So oil is flowing through a pipe. Oil is flowing through a pipe having a diameter 550 millimeters. Oil is flowing through a pipe having diameter 550 millimeters and 440 millimeters at the bottom and the upper end, respectively. So having a diameter of 550 millimeters and 440 millimeters at the bottom and the upper end, respectively. Okay? Upper end, respectively. So 550 and 440 millimeters at the bottom and the upper end, respectively. Okay, full stop. The intensity of pressure at the bottom is, if you guys are talking, you're not getting me, so the intensity of pressure at the bottom end is 370 kilonewtons per square meter. The intensity of pressure at the bottom end is 370 kilonewtons per square meter. So the intensity of pressure at the bottom end is 370 kilonewtons per square meter. And the upper pressure and the upper pressure end and the upper pressure at the end and the upper pressure at the end and the upper pressure at the end is 110 kilonewtons per square meter. And the pressure at the upper end is 110 kilonewtons per square meter. Full stop. Determine the difference in datum head determine the difference in datum head Determine the difference in datum head if the rate of flow of oil flow, are these tubes done or they haven't just been switched on? Can you switch them on? The ones in the middle. Yeah, for Pamenapa. Okay, so I said determine the difference in datum head determine the difference in datum head if the rate of oil flow through the pipe is 55 liters per second. If the rate of oil flow through the pipe is 55 liters per second. Full stop and open bracket. Full stop and open bracket. Take oil specific gravity as 0.8. 55 liters per second. Liters. All right, can you keep quiet, please? So I said 55 liters per second. Liters. Mumberacha. So, but then, you see, if you're wondering whether it's meters or liters, what units come after a flow? It's what?
Liters.
It's what?
Liters.
So whenever they say a flow of water, then that's volume per something, right? So for you to say, to even begin to think, is it liters or meters, it just means that you're not fully understanding what you're doing. All right? So take oil specific gravity as 0.8. Then you close the bracket. Take oil specific gravity as 0.8. Take oil specific gravity as 0.8. Are we there? All right, so first thing is first about this kind of a question. It wants you as an engineer, whatever you've been given in form of a paragraph, in form of whatever, how long it is, decipher it and then sketch something down about it. You see how that thing looks like? You may need to sketch something that looks like that. And I always tell students, you may maybe not get the correct answer at the bottom as you solve. Maybe you've made a mistake. But if you demonstrate from a sketch that you're able to get what was written in word form into a sketch, it shows me that you understood the question and you can interpret instructions. And this is very academic, but if you go in the industry, that's what's there. So there will be a consulting engineer. You know, this is the guy that does maybe the drawing of a structure or a road. Once he's done doing that, they find a contractor, someone who comes to read what the consulting engineer drew and they implement. So a lot has to do with what instructions were put on a sketch and how can I interpret that. Okay, so from what I get from here, one, the diameters are different, right? And then I'm hearing something is on the upper end, something is on the bottom end, and then pressures have been given. So this is how I can go about it. So one, I can either put it in this format, or I can just simply put it in that format. This also works, okay? Which one are you comfortable with? We go to the right. Okay. So let's imagine we have the bottom and upper respectively. Okay, so to me it looks like this end was bigger. Okay, and then it tapered in that sense. Because they said the diameter was 550 and 450 at the bottom and upper end respectively. We understand the respectively, right? So you can say this is the bottom end, this is the upper end. So the diameter given here, we can say it's 550 millimeters. The diameter given here is 440 millimeter. I go back to the question, what else has been given? The intensity of pressure at the bottom end is, so the bottom end is here. So I can say pressure 1 is equal to a 370 kilonewtons per square meter. This automatically means that the upper end is having something less. So I can say, if this is my point 1, this is my point 2, I can say my pressure 2 is equal to 110 kilonewton per square meter. Okay? So, the other piece of information that was given was the flow of the oil. Flow of the oil is just a discharge, right? So, it's what's flowing in here, and then I can just put it even just inside here, and then say this is my 55 liters per second. But then before you move on, there are some units that are not sitting well with the other units. You and I know that we always need to deal with SI units, right? So anything that's a millimeter, take it to a meter. Anything that's a liter, you take it to a meter. So before you even sketch and put this, to avoid making a mistake, try to convert some of these values back into their rightful units. So just do that so that you don't make a mistake. Okay, the other piece of information given is that they said the specific gravity is a 0.8 because this is oil. I will need this because my formula, my Bernoulli's equation, has a mass density, right? So I've been given the specific weight, and how do I derive a mass density from it? The question, however, says determine the difference in datum heads. We know what datum is, not so. So datum has to do with the elevations. So what they want you to do, if this is my pipe, you can simply just sketch something that is going to show a difference in datum. So we're at point 2, we can say Z2 and then Z1. They just want you to determine the difference in heights of these two. How you go about it? Well, they're assuming that you understand how the Bernoulli's equation works. And then since we're good mathematicians, we can always make one value move to the other side so that we can come up with a difference. So they just want the difference. They haven't asked you to give the value of the Z2 or the Z1, no. They just want you to tell them what was the difference in heights of Z1 and Z2. Yeah, that's the information. So the next step, once you've sort of deciphered to this level, then look at the units. What's working, what's not working. So this has to go. What's a 440 divided by 1,000? 0.44. 44. There was a time I was listening to students, and they were very confident in the answer. Can't say answer is wrong. So now I'm always very skeptical, but I hope that's the one. The 550, 0.1? Where is the 1.5 coming from? Okay. And then the discharge as well. So with discharge, I know that that 1,000 liters always gives me a cubic meter, not so, right? So a liter goes, what is a 1,000 into 55? 0. There's a zero, another zero here? Like this? Okay, so this is cubic meters per second. So with these units, I'm comfortable and I can apply them as and when I feel like. So this is the first thing that you want to do. Sketch, then put in the right units. If you make a mistake down there, always go back to the top and look for, okay, what was the thought process here? Are we together? Once you do this, you know this is definitely the Bernoulli's equation. So you begin to work around it. So one thing that I know is that P1 is always divided by plus velocity plus Z1 is equal to P2 plus velocity 2 over 2g plus Z2. The question wants me to find the datum difference. The Z1 and the Z2, these are datum heads, not so. So if I say Z1 minus Z2, then that's a difference. Not so. Yes. The question just wants me to find the difference. Not really that I should find what Z1 is or Z2, but just a difference. So if I'm able to rearrange the equation and let's say have Z1 minus Z2, then I'm headed somewhere. But then before we proceed, since you don't know between this point and this point which one is greater, and so that is going to inform which Z1 and Z2, which one moves in short. It's very possible that your answer may come out as a negative, but that should not scare you. You're just looking for the difference. Does that make sense? Yes. Where differences are concerned, the value could be a negative. It just means that you assume the wrong Z to be, yeah. Okay, so but then from what we can see, let's assume that Z2 is on a larger scale, okay? So let me rearrange this so we can say Z2 minus Z1, and this is my difference. And then whatever is remaining this side. So P1 over rho G plus V21 to G, a minus, right? So P2 over 2G plus V2 over 2G. So I've dealt with what I'm looking for. Can I find all the values that I need here before me to be comfortable with it? So, do I have the pressure? 1. I have my pressure or not so? Yes. Can I get my mass density? Yes. How do I do that? So 0.8 by 1,000, not so? Yes. Please, if you've forgotten where these values are coming from, just go back, revisit that. I think I always say that your first topic is very important. It always feeds into the others that are coming. So P1, we have mass density, not a problem. Gravity, I mean, this guy is chinso chikaya. P2, okay, let me not jump there. Velocity, do we have it? Yes, sir. So what I meant to do was this. Okay. So just also be careful how you do that. Thank you for that, sir. So if you put a negative here, it's carrying the whole lot of that side. So this whole thing is a negative, and so it should move as a unit. So either you put a negative outside, then you close. If you don't want to close it, you just want to open, you need to make this also what? But then we are good mathematicians, so this is not even supposed to be a discussion. Velocity. How can we find the velocity? we use discharge, then we also have the diameter. So velocity ingapezeke, sima amen? Awesome. So we're here. P2, do we have it? Mass density, we're dealing with the same fluid. Whatever is entering on one end is also leaving the end here. So the properties don't change. Can we get the V2? And then, this chap or answer. We can even knock off from here. Do I need to go further? Okay. Okay, so maybe according to what I'm seeing now, all these we have, let's just work around mass density and the volumes and the velocities, not so? Okay. So, okay, we can say P1, we already have it as a 370. Mass density, we said it's 1,000 by what? 0.8. V, or velocity rather, you and I know that discharge is equal to what? Area by what? Let me have your attention, Kumbuyo guys. Discharge is always equal to area by velocity. I'm looking for velocity. 1 is equal to the discharge, which I converted. If you make a mistake here, it means everything is just going to fall down. So relieve your conversion factors. So it's going to be a 0.055 divided by the area. But then you and I know that area is equal to pi diameter. What is our diameter? We're dealing with V1, by the way. All right? V1. So our V1 is here. So the importance of naming them as 1 and 2, this is where it comes in handy. Because if you don't name them, you may mix up, am I solving for 2, am I solving for 1? But since we're dealing with 1, so everything is just around here. So the diameter we found was a 0.55, so 0.55 raised to the power 2. We are good mathematicians. Our 4 will go up. So in velocity appears, amen. Who's lost up to here? It's clear. Yeah, so then from here it's just a matter of you knowing how to punch. It means that all the values that we need are there now. So we move on. What is pressure 2? 110 kilonewton per square meter. Mass density, we're not changing anything. It's just 1,000 by 0.8. Velocity 2 is equal to, the discharge is the same. So we're dividing 0.055. Where's your calculator, madam? Sorry, madam, sorry. Oh, Vasa, let me just confirm this. Okay, it's okay. All right, so we're dividing this by pi. What's the diameter at 2? 0.44. And then, of course, the 4 will go up. This chapter. So you plug in whatever is happening here. So I can say this is point number 1. You need number 2 and 3. 1, 2, and 3. At this point, nothing is missing. So your difference should be able, like you can determine what the difference is. And what will be your height? I mean, what will be your units for the difference? Just meters, okay? So when you punch, so come and leave your answer as Z2 minus Z1 is equal to, if for instance the answer is 8, just say 8 meters. Sharp. Let me remove it. I've had situations where a lecturer, just giving an example. Imamu asende ine vadi maitwara kulevo mambo kushusha na futi. No, he wrote this, I saw it. Okay, so at your own pace, individually solve, get that answer on your own, and then compare with the next person. The next time we meet, you can always show me how you, I'm still talking. Stuff being a lecture, right? Okay. So solve this individually. When you're done, compare with the next person. See, coming up with the formulas and plugging all these values is one thing. You being able to punch in and getting the right answer is different. So don't look at it and say, okay, it's simple, I can find this. So solve, see how it goes. Any questions? Yes, sir. Someone is asking a question, guys. We are almost done. Yes, sir.
There are certain books that use the mass density on the equation. Yes. So if you want to just equate the mass density on, instead of using rho g, but use the mass density, would you have to change these, or you just have to leave the units the way they are?
The mass density, like there's already a value.
Sorry,
huh?
specific gravity.
Uh-huh.
So for the pressure energies, this is P1 over rho g, but others are P1 over specific gravity. Yes. For the other equation.
Oh, I see what you mean. Yeah.
Yes. Do we have to leave them like that, or we can also change them back to like meter?
No, it doesn't really matter. So, what is asking is a very valid question. What is the unit for or formula for specific gravity? Specific weight, sorry. What's the formula? How do you get the specific weight? Mass density by gravity, not so. So it says. And sometimes this guy is just denoted as just a W. Are we together? He has asked a very important question, and I'm going to bring this because soon fakira con zero. So, in the question, everything will remain the same, except instead of giving you this specific gravity, I'm just going to say use 0.1. Sorry. What would be the difference? So you don't need to change it. Yes. So this is very important because it's feeding here. So in short, you can as well as do this if you want. But then if you don't pay attention, you mess up just on this part. So I can bring the very question. Everything, don't change anything except oh, na wakamba kujaga. But then, are you clear on this part? Yes. You're not clear? I'm happy you're not clear. I'm really happy because I'm bringing something on this. You had a different question, sir.
Yes, so which means the discharge will be changed, or how to use this. Let's say the diameter was at 550 millimeters. So when calculating for the are we going to be using 550 millimeters?
Yes, that's the cross-section area. Yeah.
So if we're using rho g, then we have to change
But then why do you want to change? So I'm saying if you're given this, you want to change into that.
No, I was trying to make clarification. If we still use that, but change the diameter to meters, we have to use the
No. You always work with the meter, sir. Always work with the meters. Understand this, madam. What's the difference between this and that? I've just replaced. And I've answered you that because I can work and play around with this just to test your understanding. So they're basically just the same. Again, you're also going back to this. Okay, guys. I think this is where our relationship ends. I know our relationship has been like most of the relationships in campuses. They only last a semester. By tomorrow, you guys are strangers. So you and I are not different, are we? So, it's been nice knowing you. You have been... Can I finish my statement? You have been great partners. It's not your problem, it's mine. I have to move on. All right. So, on a serious note, I never go outside anything that I haven't written or talked about on a board in an exam. And I know there are past papers that go way beyond the times probably I was here. And then you'd be tempted to solve there's some that you just showed me. Was it you? No, but I think that was like second question. From time to time, curriculums change. Okay, so there are some units that no longer exist, except the ones that we have right now. Okay? But then if you stick to the units that we have done, find examples on what we have done, solve as many as you can. Become great, like you don't even need to think about your formula should just be on your fingertips. You will solve questions really good. If you are bad at mathematics in terms of which one are you converting to make what the subject, work on that as well, because that is what wastes your time when you're calculating. Okay? But the best remedy, really, for me, what I've seen, just practice. The same question you've done, we have done today. Go and time yourself and see how long you're going to take today. Then maybe after 2 or 3 days, repeat the very question and time yourself. So you find that the more you have solved it, the more or the less the time you're spending on it. So those formulas are becoming more familiar to you, and it makes work easy. You have your results by next week. You're supposed to have your CAs before you write your exams. Some of my results here, no? And so far I have been marking and I am not impressed. So I was left worrying whether it's my problem, I'm not teaching enough, or it's yours. Okay? But as of next week, you will get your materials. Feel free, any question that you have maybe solved and you're not clear as a group, you can always see me whenever I'm in school. Good luck. Yeah, you've been a great class, guys. I think continue being. I always tell people this. Let me have your attention. I always tell people this, that the people that stand in front of you, if you're going to begin seeming troublesome, or you will get what you would have put in. I have my own stories of at one point where we met Madam Handongwe. She's the one lecturing you, right? Yeah, she taught me. That lady taught me. We got upset and our results were terrible. People came for SAPs. There were people that reached third year and they were still writing surveying. You know? So my point is, you get more respect with how you respect the person standing in front of you. For instance, Nikamba, that dude just walks out. Like, he just walks out. Like. So as a person, I'm thinking, oh, okay. So it's like we are throwing jabs at each other. So, but you don't do that. The best you can ever do for yourself and your career, you have so much to lose than a person standing here. Because if he says you're not going anywhere, or you are repeating that course. So sometimes just lick people's boots just to run through. Just understand the course. Even if you don't like the course, you don't like the person, but like the course, you want to clear it so that you can move on. Time is very precious. You don't want to start repeating things that you've already been taught and things that were so much easier and obvious. So I always preach because it's not just me standing here, okay? So all the best. We are likely to meet in third year. Huh? How about that? Because I have classes with the first years and the third years only. Second years, nah. So a whole 1 year, I will forget your faces. And don't feel offended if we bump anywhere. Muni Posha, I'm not even looking at you. I see and I look at so many faces. Okay, so yeah. All right, so all the best and we'll see you in exam. Here, I'm the best.